Hi everyone, my name is Loes Olde Loohuis. I'm faculty here at UCLA in the departments of Psychiatry, Computational Medicine, and Human Genetics. So Shamani was just talking about Columbia EHRs with a U. I'm going to talk about Columbia EHRs with an O or with two O's. So we'll see how your personal LLMs are going to handle that very subtle but important distinction. All right, so I study psychiatric genetics. And what I'm going to talk about today is some of our efforts in phenotyping precise psychiatric phenotypes from EHR, and specifically from clinical notes in the EHR. So, oh no, I really don't like. Oh, it's better here than there. Okay. So phenotyping in psychiatry is really challenging. And I like to illustrate this with this picture of a person sitting on a bench. This was a New York Times article that was titled, "Waiting for Depression to Lift." And I think it so well sort of captures that it is really hard for us to know whether this person sitting on the bench is depressed. We don't have any good biomarkers for psychiatry. We cannot measure anything about this person's body, knowing whether they are depressed or not, at least not very accurately so. And let alone knowing whether their depression is lifting. Is their depression getting better? Is it going away? Or is it taking a turn for the worse? And that it's really hard for us to know. And so it's a difficult question. And so some of the questions that we are working on in my lab and that I'll talk a bit about today is, can we use AI to extract meaningful phenotypes from electronic health records? Can we integrate different sources of data? I won't talk so much about that today. And then once we can do that, can we measure progression to perform clinically meaningful prediction? So I already kind of alluded to this a little bit. Here's, as an example, there's two types or two different trajectories of depression. One, maybe the top person is somebody whose depression is lifting. They start out being depressed. It's getting better and disappears over time. Whereas the bottom person might be somebody that starts with depression, but later has a manic episode and develops what is called bipolar disorder. It's a disorder characterized by both episodes of depression and mania. So this particular problem of people starting off their diagnosis with depression and later developing bipolar disorder is really difficult in clinical practice. On average, it takes about 5 to 10 years from the illness onset to receive a diagnosis of bipolar disorder for bipolar patients. During this time, this sort of waiting time, patients receive suboptimal treatment, such as only antidepressants without mood stabilizers, which can lead to increased suicide risk and overall poor outcomes. And so one of the goals that I have in my lab is, can we predict who will develop bipolar disorder and whose depression will lift? Okay, I already mentioned we're going to go to Columbia, the country, with two O's. If there is one thing, no, that's not true. I want to achieve more things in my career, but one of the things I hope to achieve is that people recognize that Columbia, the country, is written with two O's. Okay, so in Columbia, we are building a biobank for severe mental illness. And we do this in the Paisa region of Colombia. It is a very beautiful region. It's set between two mountain ranges. It's where the coffee grows. It's when you think of Colombia, maybe in your head, you might be thinking of the Pisa region. And it's a very interesting and exciting region for genetics research. I won't be talking about that today, but it's a population isolate, and it currently comprises 9 million individuals that live there. So we're building a biobank for severe mental illness. What does that mean? We are in the process of recruiting 100,000 participants. We're currently at about 87% complete. Those 100,000 participants are comprised of 50,000 patients with severe mental illness. With severe mental illness, I mean bipolar disorder, schizophrenia, of severe recurrent depression. And those patients are being recruited from 4 psychiatric hospitals. So all the participants in our study receive care in a psychiatric hospital. So they're really on the severe end of the spectrum. We're also recruiting 50,000 controls from Sura, which is a health insurance and healthcare provider in the region, similar to Kaiser, what we have in the United States. And to be able to do this at this scale, all the phenotyping is using electronic health records. So we have EHR of about 400,000 psychiatric patients from these hospitals, and the patients for the controls are being selected from Sura, which treats about 5.3 million individuals in the region. Something additional that is cool is that 20% of the cases also have Sura insurance. So in that case, we have both types of insurance. And yeah, I'm not going to talk about genetics today, but for all these participants, we're getting blended genome exome sequencing. It's a mix of low-pass whole genome sequencing and deep exomes. Oh, that's actually outdated. We're a little bit more than 34,000 completed by now. Mission Origin is one of the largest genetic studies of severe mental illness in the world. I like to show this picture. Those of you who have seen me talk have seen this picture, which shows the biobanks in the world, I guess. It's a little outdated by now. I really need an update for this. But the x-axis is the year that the biobank started recruitment, and the y-axis is the proportion of participants that are not of European ancestry. And one thing that you might notice is that purple is South America, and there was no purple dot on the map up to 2020. And so with Mission Origin, we're putting a purple dot on the map, which we think is very important for the global goal of advancing precision medicine, but also increased health equity. All right, that's Mission Origin. I already mentioned that information, or I didn't quite mention it, but I said it's really hard to phenotype patients with mental illness, using measurements on their body. And therefore, what is really important in the EHR to know how the patients are doing is the clinical notes. And the clinical notes are incredibly elaborate. They really describe symptoms, behaviors, course of illness in these psychiatric hospitals. And so one question that we have is, can we confidently extract these symptoms from the notes, such as delusions, suicide, sadness, etc.? And so to do this, we selected 139 psychiatric phenotypes that we were going to try to extract. And these are a broad range of phenotypes, and they are very, very fine-grained. So we have different types of delusions, different symptoms of sadness and depression, anxiety, cognitive features, etc., etc. And so we developed a pipeline to extract these symptoms from the text. To get a gold standard, or to get initially training data as well as truth, we had 2 clinicians. We selected 2,000 documents from 2 hospitals, but in this case, I'm only going to talk mostly about one of the hospitals. 2,000 notes, basically, and we had clinicians phenotype tag all of these notes. So they read them, and they they selected whether any of these 139 phenotypes were present and where they were present in a note. This was an incredible big effort. In addition to the notes, we also had 120 patients that were fully evaluated. Their entire EHR was evaluated by these clinicians, because sometimes you might imagine that you can see a symptom sometimes you might imagine that you cannot see a symptom in a specific text piece or in a sentence, but you know when you read the chart that this patient was delusional. And so to account for that, we also had full patient evaluation of 120 patients by 2 clinicians. And initially what we did, here's a picture of how the phenotype tagging worked. So you have a sentence, and in that sentence, we have a bunch of phenotypes present, like irritability, insomnia, psychomotor agitation, aggressivity, and the clinicians phenotype tag all these symptoms. And so initially what we did is something very simple. We started this process before LLMs became available to the public. And so what we did is we basically said we take all the phenotype tags and we see what patterns make up these phenotypes using SPACY or like more traditional NLP. We also then accounted for whether something was negated or other types of context. A sentence might have a delusion in it, but be talking about a family member, or be talking about the past, or be a warning about the future. If you have delusions, come back. So we captured the phenotype itself as well as the context. And so this worked really quite well. We only included phenotypes with sufficient inter-rater reliability. Like if 2 clinicians cannot agree about the phenotype, we cannot expect to extract it with high accuracy, as well as sufficient support in the training data. We set our minimum threshold to have at least 10 instances to be able to extract it. And so here on the y-axis, you can see F1 score. On the x-axis, you don't have to read this, are the phenotypes, and they're ordered by how well they can be extracted using this method. And so very often we get an F1 of greater than 0.8, which in our mind was good enough, which is really highly accurate. You can also see that on the left, there are some that we missed because we couldn't evaluate them. They were not frequent enough. And so overall, we get an average F1 of 0.85 in those phenotypes. I think there were 88 that were left, and 72 of those we were able to extract with high confidence. And so we thought that's great. But of course, the next question is, did we need to do all this way? Could we use LLMs to extract these phenotypes? And this is a project that was led by Clara Friedman, who really, took on this project and took full leadership of it. I invited her to come today, but unfortunately she's not feeling well. Otherwise, you would have had a chance to meet her. But basically what we did, we had the test set from our original effort, and we basically started with zero-shot prompting. So we just asked the LLMs. We picked 11 LLMs that were open source because we have to be able to put them on the server where we have the EHR. And we asked, does this document contain the phenotype X? And where X can be, anxiety, abulia, all these psychiatric phenotypes. And so on the x-axis here, you see the 11 LLMs that we used, and on the y-axis, you see the average F1 score that we obtained from doing this using LLMs. And so just a reminder, for our traditional NLP, we get to about, we get to about 0.8. And so this is how the LLMs work with zero-shot effort, and they really don't work very well. They're not good at this. And I don't show that here, but the reason they're not good at this is that they are hallucinating, which is almost like a pun when you're actually trying to extract hallucinations. But they find a lot of positives that are not there. And we can look at the comparison between our traditional NLP as well as the LLMs. And here are all the LLMs sort of performance on the same plot. And you can see there's a lot of stuff going down at the bottom where the LLMs are really not good at doing this task out of the box. We do also see some of these bowls are above the spacey traditional NLP. So there are some phenotypes that we rescue even out of the box. And for those, especially some of the rare ones can be rescued out of the box. But in aggregate, it didn't really work out. So the next step in this endeavor is to see if we can if we do few shot prompting. So we give each of the LLMs a couple of examples and say, this is actually what we mean when we say, this is the phenotype. And so we gave up to 5 examples to each of the LLMs for each of the phenotypes and then try it again. And what we can see is that this improves the performance overall. These bars are now higher. But we're not really close to, to the goal is what we're trying to achieve, which is about 0.8. All right, and so then finally, because we had our training data, we had these 2,000 nodes that were completely annotated. We said, what if we just fine-tune these LLMs? Using the training data that we have. And so we give them all this fine-grained information that we had aggregated. And so that's what we did. We fine-tuned all of these models. And lo and behold, the fine-tuning dramatically improved performance. And so even though we had only 2,000 nodes, this really, really helped the LLMs being able to extract these phenotypes with very high accuracy. And this is what we get after fine-tuning. And so to me, this was surprising. I don't know if this was surprising to you. To me, this was surprising because I thought that's not a lot of data. These models are so big, some of them. How come they learn so much from so little? But they really do. And now we are on par with performance of our traditional model. And we've rescued, in fact, we get improvement above many of the phenotypes that we weren't able to extract in the first place. Here I ordered the phenotypes in a different order, not by how well we originally were able to do that with TNLP, but how common are these phenotypes. And we find that indeed more common, there's more robust performance, and all the LLMs can extract the common ones. As it gets more rare, so there's less support in the training data, it's much more flip-floppy, and it depends on the specific model. We also see that for some of these traits, specific LLMs perform poorly or well. Poor is easier to see, like, for example, poor adherence. That just doesn't work for one of the Quen models, but it works well for the other models. Whereas some of the phenotypes are just really hard to extract, such as adverse effects. You can imagine adverse effects is a little bit of a broad term that may be hard to detect, even though it's common. Okay, so great, we can fine-tune LLMs to be excellent at extracting phenotypes. And in total, we can now extract 100 phenotypes at an F1 of greater than 0.8, which we are really happy with for our goal of, doing psychiatric genetics and understanding psychiatric course of illness. But there's a problem. One of the problems is that we cannot share these results with the community. We've trained it on our actual texts. And because of the leakage or the data leakage that goes into these models, we cannot put that model out there into the world and say, now you can extract psychiatric phenotypes, because it's trained on our EHR, and it might encode some of the information encoded in the EHR. And so then we came up with an idea, which we came up with the following idea. I wouldn't put my judgment on it just quite yet. So we thought, why don't we use the real annotations, like the actual parts of text that were annotated, and create fake notes, fake documents, using an LLM, in this case using Llama, and then use these fake documents to fine-tune the LLMs, to fine-tune an LLM. So now we have only used the annotations itself and not the whole text, and so we're sure that there is no PHI, no personal information encoded in them, so we can safely, and then ask Llama to say, hey, pretend you're a doctor, create a note, use these phenotypes, and then we take those notes and fine-tune another LLM. We could see if we could extract these phenotypes just as well. So, yeah. I don't know if you guys think this is going to work. I didn't think this was going to work, but maybe I'm a pessimist. So it turns out this works. This works really well. So we used one of the Mistral models because it had really excellent performance, and it was one of the smaller models that was excellent. Because obviously when we share something with the community, we want to share a model that can be used in as most different contexts as possible. So including people that don't have the kind of resources to run ChatGPT or the very, very large Llama models, but rather the smallest model that can do the job. Okay, so we took one of the Mistral smalls and trained it completely only on synthetic data. And what we find is that it basically performs the same. So that works. And we can now share this model with the community, and it can be used in research, in more research. You still need to run an LLM, but the setting doesn't need to have that many resources. You don't need to do the fine-tuning yourself. So we're very excited about this. Of course, the fact that we can share it with the community doesn't necessarily mean that it's generalizable to other kind of texts. And so that is where, our sort of second hospital comes in, because we wanted to actually test whether if we train it entirely on one hospital, does it work on the other hospital? And I should mention that the two hospitals, I didn't walk you through the entirety of this figure, but we have two hospitals in gray, Clínica San Juan de Dios Manizales, that's where we did all our work. Olmo is another hospital, and they're very different. One of them is a private hospital run by a Catholic institution. The other one is a public hospital. It's the largest public hospital in the region. It is huge in general. So there are some quite big differences in terms of the patient population, treatment, etc. And so we were wondering if we train it in one hospital and then apply it to the other hospital, how is that going to work, even though they're quite different settings. And so here now you have two bars. One is the original performance on Manizales Hospital, and the darker bar is using that same model, no other modifications, run on the public hospital, Olmo. And we find that, yeah, there is a drop in performance, but overall these models generalize really well. Even the one that is, the synthetic, that was trained on synthetic data. So we can use LLMs to extract phenotypes, and we can build generalizable models that we can share with community. So now we have all the parts that we really wanted to have together, and you know, that's really exciting. So now that we have the phenotypes, we can use them, right? We can use them to better understand the genetics of severe mental illness, but generally mental illness. So for example, we can look at phenotypic profiles by diagnosis. Here I put 3 main diagnoses: depression, bipolar, schizophrenia, and I can see for each of these phenotypes, how common are these observed in patients with these diagnoses, stratified by sex in this case. We can also look at phenotypic profiles, you know, more globally. Like in this case, we took an MCA, which is kind of like a PCA for binary data, for categorical data, and we can see where do people fall on the phenotypic spectrum using all these phenotypes that we have. And in this case, we have, again, the same colors. In the top, we have each dot is a patient, and you can see that blue and red are bipolar, depression and schizophrenia. They're kind of separate. People with depression and schizophrenia are different in their phenotypic profiles. But the green is bipolar disorder is all over the place. And we can look also where, you know, instead of looking at individuals on the space, we can look at the phenotypes on the space and where do they belong. We can also look at phenotypic profiles geographically. And this is work that is under review that's done by Greta. And here I'm just going to show this one slide. It's just a small vignette, but just to show you like the power of having these phenotypes. So here what she did, she was very interested in studying barriers to seeking care. And so she looked at, are the people that live further away more severe when they come in? So they have to travel more. Do they only come when their profiles are more severe, their phenotypic profiles? And that turns out to be the case. So each of these blocks are one of the phenotypes. The x-axis is travel time, so between 0 and 6 hours in this case. And so we're looking at, these are rates, I guess, of rates of observing the phenotype depending on how far you have to travel. And you can see if you have to travel further away, you're more likely to have delusions, hallucinations, grandiosity, suicidal ideation, depending a little bit. The 2 colors, I recognize now that there is no legend here. I apologize for that. The 2 colors are socioeconomic status. So as measured using health insurance, type of health insurance. I won't have time to go into, but that's very linked to socioeconomic status in Colombia. And so lower socioeconomic status, for lower socioeconomic status, the patients with lower socioeconomic status tend to be more severe when they come in, and in some cases also more affected by travel time. And so we can see all these things just by having the notes and by having where patients are coming from. But I want to go back to the person on the bench and the question, can we now measure if they're depressed? Can we now measure if their depression is lifting? So here's an example of just, I think, about 10 patients and their visits over time. So each of the little blocks is a visit. And we've just here selected, this is just for illustration, a few of the phenotypes that we can now extract related to depression, mania, and psychosis. And you can see, for one, you can see that there's many different phenotypic profiles and many different phenotypic trajectories over time. These are all patients with a depression diagnosis. But here's a patient that might look like their depression is lifting. So Initially, they come in with a red block and an orange block, which indicates suicide attempt and suicidal ideation. They come later with depression again and with another suicide attempt. But then later the blocks, at least on this, using these however many phenotypes, 9 phenotypes, those phenotypes are no longer observed. Here's a patient that is a classic patient that switches from unipolar depression to bipolar disorder. They start off with depression, 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 and then later they have green symptoms, which in this case indicate mania. And so one of the questions that we ask is, can we predict some people starting off with depression who's going to develop mania, or who's going to develop bipolar disorder? And we did this actually, and I should say I'm turning things around a little bit because we did this when we only had 4 symptoms. Now we're redoing it with all of our symptoms. But even with the 4 symptoms and structured data in the EHR, based on 13,000 individuals that start with unipolar depression, we are kind of able to predict who's going to convert to mania within the next 5 years. So an area under the ROC curves with an index of 5 years here is about 0.68 to 0.70, depending on exactly the model. And you might think that's not good, like that's not really good, because you see a lot of very good area under the ROC curves in this week, or maybe in these 3 weeks. And I like to argue that it's actually quite good. Like, if we allow for a false positive rate of 50%, we're able to recall 77% of patients that will switch within 5 years. And this is a really hard problem, right? This is a problem that clinicians cannot do. And so even being able to recall that number is something that is very encouraging to us. It's not yet great. I recognize that, and we can probably do better. And so hopefully the next time I'm standing here, there will be an update to this as well. Okay, so sort of wrapping this up, we can use AI, we can use LLMs to extract meaningful and precise phenotypes from clinical text. We can develop models that can be shared with the community and used in resource-constrained settings. We can predict patient trajectories, predict whose depression will lift, hopefully, or will take a turn for the worse, such as through a conversion to bipolar disorder. But we can probably still do better. So Mission Origin, I'm very excited about it. We hope that it will power genetic discovery and identify causal variants, not just for diagnosis, but for specific symptoms as well. We are excited about characterizing risk for severe mental illness, the relationship between genetic and environmental risk, and perform some of these longitudinal analyses of disease trajectories, such as diagnostic switches, but also treatment response and understanding course of illness. We're currently at 88% recruitment. You see within the moment of this talk, we went up by 1%. I mean, that's just a joke. We're just very close to being between 87 and 88, at about 40%. Although I wouldn't be surprised, honestly, like the recruitment team is amazing. And 40% we have sequencing complete. Sequencing is happening all the time now. So, yeah, I was doubting before when I was sitting here whether I should include this slide, but I do it anyway. Being a scientist is challenging, especially these days for many of us. And sometimes it might feel like we're this person sitting on the bench where somebody's taking away the things that we've built, and it's just like being erased from under us. if you feel that way, I feel that way sometimes, I would like to say doing it together is better, and I'm very grateful for having CGSI. I love coming here. Somebody said yesterday, oh, Loes has been at UCLA forever, and it is true, and I've been giving talks here forever, but also I'm just so grateful for this community and the vision of Eliezer and others and all the staff for putting this together year after year, because I think it grows not just science, but also friendship and community. So I'm happy to see that again and again, and this year again, seeing sharing of ideas and community grow. And so, yeah, thanks for that. But yeah, I also want to thank my collaborators. These are teams in Colombia. They are truly amazing. For Mission Origin, I like to mention that every individual that is a participant gets approached by one of our project members to ask if they want to be part of the study. It is not easy to recruit patients with severe mental illness, and it's an incredible effort. And without them, there wouldn't be no Mission Origin. So that's amazing. I also want to thank my lab, especially Clara, who did most of the work on NLP. Juan, a former student, started off this effort. And I already mentioned Greta, who is studying barriers to seeking care. My collaborators, Nelson Freimer and Carlos Lopez, with whom I lead Mission Origin. Danielle Maria as well, for doing a lot of the phenotype annotation and my funding. And with that, I'd like to open it to questions.